So the diagram below shows Newton's laws of motion. So we have to study the diagrams carefully and answer the questions that follow. So what is the first question? So we have to explain the law of motion shown in each of the diagrams A, B, and C above. So what are the laws of motion? So for diagram A, the answer is Newton's third law of motion. Newton's third law of motion. And what does that law state? It states that for every action, there is an equal and opposite reaction. So you can see that as the man squats whilst lifting that heavy object, there is an opposing force, that is a reaction force, that is opposing his direction of movement. And this law means that force always come in pairs. So if object A exerts a force on object B, then object B exerts an equal but opposite force on object A. That is the force of motion, or that is the law of motion shown in A. What about B? B has to do with Newton's first law of motion. So the Newton's first law of motion states that an object stays at rest and an object in motion also stays in motion at a constant speed, or in other words, at a constant velocity, unless acted upon by a net external force. That is what we see in diagram B. And what that means is that the ball will remain on the table as long as no external force acts on it. It will always remain on the table until someone applies an external force on it that is able to overcome the normal reaction and gravity. So that is that second diagram. Now for the diagram C, the third diagram, that's Newton's law of motion, the second law of motion. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. It is this particular law, that is Newton's second law of motion, that we got the formula for force, that is mass times acceleration. So this means that force is directly proportional to mass and at the same time directly proportional to acceleration. So the product of mass and acceleration gives us force. That's Newton's second law of motion. Now our second question is this: give one application of each law in everyday life. So for diagram A, the third law, Newton's third law of motion, that to every force there is an equal and opposite reaction. So that is saying in swimming. So when you push the water backward with your hand and feet, the water pushes you forward. So you push the water backward, the water pushes you forward. So there is an opposite and equal reaction. You push it back, it pushes you forward. That is Newton's third law of motion. Now for the diagram B, Newton's first law of motion, that is basically an object at rest remains at rest, and an object in motion also remains in motion. So that is a typical application is when riding a car. So when you are in a car or a moving car and the driver suddenly applies the brake, you would realize that the passengers jerk forward in their car. This is simply because the passengers want to keep moving forward with the car, but the driver suddenly applies the brakes. So by applying the brakes, the driver is saying, hey, hold on, let's stop, but the passengers want to keep moving. And the opposite is the same. When a car is stationary and then the driver suddenly starts the car and moves forward, the passengers jerk backward. That is also a real-life application of Newton's first law of motion. And now for the third diagram, that is Newton's second law of motion. How it's applied, or where we see it in our daily life, is the harder I push a trolley, the faster it accelerates depending on its mass. So the mass of an object is so important when applying force to it. So if an object is this small and less massive compared to a bigger object that is more massive, if you push the two of them, depending on their masses and their force applied, that will show how much it will accelerate. Now let's move on to our next question. This has to do with calculation. So if the car in the diagram C accelerates at 0.3 meters per second squared with a force of 300 newtons, we have to calculate the mass of the car. Remember, in Newton's law of motion, the one that has to do with force equal mass times acceleration. So that's what we are going to use. So force equal mass times acceleration, where F is the force applied. And the question, the force applied is 300 newtons. And the acceleration is 0.3 meters per second squared. So let's put these values into the formula. But before we do that, let's do a little bit of change of subject. We have force equal mass times acceleration. That means mass is equal to force divided by acceleration. Meanwhile, force is 300 newtons and acceleration is 0.3 meters per second squared. Dividing 300 by 0.3 gives us 1000 kilograms. So that is the mass of our car. The supposed mass of the car we have in the diagram. Is there any other question? That's the last, I think. So you have to explain how the moving car in C will attain a state of balance. A state of balance, at what point will it attain a state of balance? So for the moving car to attain a state of balance, that is also known as the state of equilibrium. What that means that all the forces acting on it must be balanced. That means there will be no net force acting on it. So the man is pushing. There are other types of forces. There's gravity, there's normal reaction, there's friction before the man is applying his force. If the net force of all of these forces cancel each other out, then we will say that the net force is zero. Or in other words, it's at a state of equilibrium. It's balanced. So the car will then attain a state of balance. Unless otherwise the net force is not zero, then it's not in a balanced state. So this brings us to the end of this particular question. So what are we to expect in our next video? So in the next section, we'll be answering a question on food chains and food web, or more specifically food webs. So come back again to have a view or have a lesson on how to answer these kind of questions. See you in our next lesson.